This is lecture 10 of Logika računalništvu, Logic in Computer Science. Today's lecture is slightly different from usual in that the purpose this week is, rather than introducing new material, I'm going to present a solution to the LTL model checking exercise that is, along with this lecture, being released on the course web page. So let's have a look at that exercise. Right, so here's the exercise that you've seen, and what we have is a formula phi in LTL, linear time temporal logic, and our purpose is to model check this formula in two different rather simple transition systems. It's also a rather simple formula, and of course that's not really a very difficult thing to do. One could perfectly well do it by hand and just have a look and basically see whether the formula is true in each of the two, along every run through each of the two transition systems. But instead, the purpose of the exercise is to help you understand the model checking algorithm, and this means simulating the model checking algorithm by hand. Now, before doing this, just a couple of words about why one might simulate an algorithm by hand. Of course, it's not a very useful thing to do. The whole point of algorithms is that computers run them, and they're rather tedious things to simulate by hand. So the purpose of covering the material on this course is to give you some kind of a feeling for the clever algorithms and technology that go into the applications of logic and computer science. So model checking is really a practically useful tool that is used in industry, and there's been a lot of work on design of algorithms, and I think these algorithms are non-trivial. The one we're considering is an old algorithm. It's not at all the kind of efficient algorithms that actual model checkers use nowadays. But anyway, one of the goals of this course is to introduce you to some of this non-trivial mathematical technology that is used in such practical tasks, such as model checking. So on the lecture log, I'm going to put a link to a video, which is of a talk by Edmund Clark, who was one of the founding fathers of model checking, who received about 12 or 13 years ago, the ACM Turing Award for his work on model checking. That's the Turing Award is like a sort of Nobel Prize in computer science. So model checking is a seriously recognized contribution in computer science, and the lecture that Edmund Clark gave is, I think, quite a nice summary of model checking and its applications, and some thoughts about the future, which was the future 12 or 13 years ago. But anyway, it's still an interesting lecture. So that will hopefully give you a bit more background. The rest of today's lecture then is going to be to basically do the exercise, the LTL model checking exercise, which is here, where we have a particular formula and we are supposed to answer questions A to F about this formula. So the first thing is to understand the formula phi. So basically throughout the lecture today, phi is going to be this one particular formula. And to understand this formula more easily, using the F and G operators so that we can understand what the formula says. So phi, let's write phi down. So phi is the formula true until not true until Q. Let me just double check that I've got that right. So we go to true until not true until Q. Yeah. So part A is we want to understand this formula more easily in simpler terms in terms of the F operator and the G operator. So the way to do that, this is very straightforward because we recall that the formula F of any formula psi is equivalent to true until psi. Because F psi says eventually in the future psi will hold, and this says true holds, which of course it always does, until psi holds. But remember that the until operator has this, it's a strong until in that it for it to be true, it requires psi to actually hold sometime in the future. So this is the same thing as future psi. And so we then see immediately that, so phi is equivalent to, well, we've got a true until and another true until. So it's future, not future q. So this is one answer. Put a box around it. So sometime in the future, it will be the case that it will no longer hold in the future. Sometime in the future, it will happen that for no further time in the future, Q will hold. But if we want to move the negation around, which we may or may not want to do, this is already a perfectly sensible answer to the question, but still we might want to move the negation around, so we might recall also that G of psi, so that's globally in the future psi, this is the De Morgan dual, if you like, of the future operator. So it's the same as it's not true in the future that not psi. So using that, we can get that phi is equivalent to F G not Q. So there is some time in the future from which always further on in the future not Q holds, or it's also equivalent to not G F Q, which says it's not true that Q holds infinitely often. So these are also perfectly acceptable solutions. So there isn't just one possible answer to this question, but a whole range of answers. And we've rephrased phi so many times that I would say we've got quite a good understanding of the property phi. Okay, so that was part A. Let's have a look at where the question goes from here. To go back to the question sheet, that's what we need. Okay, so the next thing to do is to determine the set of complemented subformulas of the formula not phi. So in the notes for lecture 8, I've got the amalgamated notes of lectures 8 and 9 here. We saw that we were defining complemented subformulas. We assumed that formulas contain only the following logical connectives, so negation, disjunction, true, next, and until. And then I defined the notion of the set of complemented subformulas of a formula. So you can remind yourselves what that definition says. I'm not going to explicitly refer to the definition now, go back and forwards between the definition because that would be a bit tedious, but we want to look at the set of complemented subformulas of the negation of phi, which is this. Notice that this formula already is in the the form that it only uses the operators that we've restricted to. So it has the true and it has until, and those are the only operators this one has. So it is already in the restricted language that the definition of complemented subformulas was defined for. So let's go to here. We want to have, oops, I want to be black. So the complemented subformulas of not phi, which is not true until not true until q. That's quite a big formula. So the set of complemented subformulas, they come in pairs, a formula and its negation. So we have not phi and the negation of not phi, which is phi. So I'm going to write them in their pairs. So we have phi. And its negation. And then we've got an until operator in phi. So we have either side of the until operator and their negations. So we have true and not true. And we have not true until q. Let me put this on the right hand side because it's a negation. Not true until q, and its negation true until q. And then again we've got an until operator, so we have either side of that and their negations. So we have true and not true, but we've already got those, and q and not q. And this is the set. If we want to actually write it as a set, I mean, for this, since this is not a course on set theory, one doesn't need to be fussy about this. So this would be a perfectly good answer to an exam question like this. You wouldn't need to put the set brackets, but anyway, let's just put set brackets in just to make it look neat, or not. Anyway, there we go. It actually looks less neat, but we've now got our set of 8 formulas. I actually want to just do something else before moving on, which is, although I had defined the set of complemented subformulas assuming this normal form in which every formula only has the certain operators, true, until, disjunction, negation, next. Those were I think that was all the operators we were allowed. So the reason for doing that was in order to not to have to give too many cases in the lectures in weeks 8 and 9. But in practice, one wouldn't really always convert into this form in which you write the formulas using only these connectives. In practice, one would often work with the formulas with other operators instead. So let me just tell you how that would work if one was doing it. So just for comparison, I'm going to talk about the set as one would define it of complemented subformulas of the negation of phi, where phi is in this form here. Future phi is in the form future not future q. So one could perfectly well, if I hadn't defined everything just for this small set of connectives in lectures 8 and 9, one could perfectly well work with a more concise version of phi like this. And then the set of complemented subformulas would be constructed using exactly the same principle. So it would be, so again, for every negated formula we put, well, for every formula we put it and its negation. So we would have the formula not phi itself, which is not f not FQ, and its negation, which is F not FQ. We've now got a future operator, so we just include the argument of the future operator, which is not FQ, and its negation, which is FQ, so we would have not FQ and FQ. We now got a future operator again, so we include its argument and its negation, so that would be Q and not Q. So we see actually we've got a smaller set of complemented subformulas if we deal with this more concise version of the formula. Okay, so let's go back to we've answered question B now. So let's go back to our question. And question C is now to determine the elementary subsets of the complemented subformulas of the negation of phi. Right, so this is where things get a little bit fiddly. So let's go to the notes from lectures 8 to 9. So once we had the complemented subformulas, we had the notion of an elementary subset. And some important considerations were that for every complemented subformula, exactly one of that formula or its negation needs to belong to an elementary subset. If you have a disjunction, one of the disjuncts needs to belong. If true is a complemented subformula, it needs to belong to the elementary subset. And some awkward things for the until operator that so if the destination part of an until operator, that's the thing on the right, is in the set, and the until is a complemented subformula, then the until is in the set. And if an until is in the set and the destination part is not in the set, then the source part of the until operator. I'm not sure whether source and destination are very good names here, but anyway, the left-hand side of the until operator is in the set. So these are slightly fiddly rules. Let's try to remember them, but we can be guided by the principle that the elementary subsets are exactly all sets of formulas that can be true at the same time at a state in a run through a transition system. So for example, if phi prime is true at the state S, if psi prime rather is true at the state S, then psi until psi prime is vacuously true because the destination part, as I said, the right hand side is already in the set. So if that's true, then the until it is true. So if that's a complemented subformula, that needs to be in the set because we know that complemented subformula is also true by virtue of psi prime being true. Right, so let's go back to. So we want to do the set of the elementary subsets. So there's going to be C. The elementary subsets of the complemented subformulas of the negation of phi. Right. So here we have our complemented subformulas, and our elementary subsets are going to contain, for every formula in the complemented subformulas, we either have it or its negation. So for each line here, we need one of these formulas, either the positive formula or the negated formula. And we include all the subsets that contain exactly one formula from each line that satisfy the rules for the elementary subsets. Now, one of the rules was that if true is a complemented subformula, then true needs to be in the set. So true is going to be in all our sets, so the negation of true will never be in any of the sets. So we can start our first set with true. And we're going to see which other formulas we need to put in it. So I find it easiest to work from the simpler formulas towards the more complicated formulas. So we need one formula from each row. So the next simplest formula is the Q and not Q row. So we can either put Q or we can put not Q in with true. There's no rule to tell us which of those we put in. So let's try putting Q in first. So this is saying we're considering a state in a run now in which Q holds. But if Q holds, then anything until Q holds. And since true until Q is a complemented subformula, we need to put that in. So we can't put its negation in because we're forced to put true until Q in. This was one of our rules for the until operator, that if the right-hand side holds is in an elementary subset, then so is the until operator, as long as that until operator is one of the complemented subformulas. So we have true until Q. And we've just got this row at the top here. So this time, we don't have the right-hand side. So it can either be the case that true until not true until Q holds, or its negation can hold. Both of those are consistent because true belongs to the set, so both of those are consistent with the other formulas. So we have, in fact, then two possibilities here. We have true until the negation of true until Q. And we're also going to have another complemented subset, another elementary subset, true until Q, with the negation of this, not true until not true until Q. Okay, so those are the only two possibilities where we have Q in. So let's now look at the possibilities where we put not Q in. So if we put true and not Q, well, we can still have true until Q. We're not forced to now, but we can still have true until Q. And then again, if we have true until Q, we can again have true until not true until Q. And we can have true, not Q, true until Q. And we can have the negation of the larger until again. Not true until Q. And finally, if we have true and not Q, we weren't forced to put true until Q in, so we can try what happens with the negation of true until Q. But now, we've got the negation of true until Q. This is the right-hand side of an until. So if the negation of true until Q is true, then true until the negation of true until Q is true. So we're forced to put in here true until the negation of true until Q. So we can't put the negation of this formula in. And that's it, because we've explored every opportunity that, so every time we were forced to do something, we've done it, and we've explored what happens if we have true and q, and true and not q, with true until q, and with not true until q, and we've exhausted all the possibilities. So we have 5 elementary subsets there. Let me just remark that we could equally well do this again using the formula using the formula that uses just the future operator, so not future q. And for this we need to know the rules. So let's put these in red. So the rules are, so if psi is in a set S that we're trying to see if it's elementary or not, and f psi is in the complemented subsets of the complemented subformulas of the formula we're considering, then f psi also belongs to S. So because if psi is true now, then it's vacuously true that it's true in the future. So if we've got that psi is true, then f of psi should also be true, as long as it's one of our complemented subformulas. And if the negation of f psi belongs to S, so if we're saying that psi does not hold in the future, then certainly psi does not hold now, so also not psi needs to belong to S. In this case, not psi is automatically a complemented subformula. And using these rules, we can work out the complemented subformulas, the elementary subsets of the complemented subformulas directly. And so, for example, if we start off with q being true, then f of q is forced to be true, and we can have then that. So let's have a look at our complemented subformulas. So we've either got f not f of q and not f of not of f of q, and either of those can hold, so by these rules. So we can have f of not of f of q we can have q f q not f not of f of q, and then we can consider what we can have with q and not fq, and so on. What I'm going to do is I won't complete these now, but I will complete this after the end of the recording, so that you can have it in the notes as well, so you can see what you get. And we will get, maybe it shouldn't be surprising, but here we've got q. This is the same as f of q, and we'll see that the sets, we're going to get exactly the 5 same sets, but just with the notation, with a more concise notation using the future operator. Okay, let's move on. And what was that? That was part C, so now we're on part D. And so part D is, let's go to the exercise. Now we want to construct the generalized non-deterministic bookie automaton for the formula not phi, and then simplify it. But before we simplify it, let's construct the thing itself. So what we're going to remember firstly is that the generalized non-deterministic bookie automaton, its states are the sets of complementary subformulas. So, sorry, are the elementary subsets of the set of complementary subformulas. So the states are going to be those 5 sets we've constructed above. So let's write them out again so that we can connect them to look like a bookie automaton. So I'm going to miss out the true because that's not really needed, because we know that it belongs to every. So let's leave some space. So we had Q true until Q, and let me just check, and true until not true until Q. We had Q true until Q, and the negation of true until not true until Q. We had not Q true until Q, and true until the negation of true until Q. Sorry that it's a little bit tedious writing these out, but basically I'm copying these states with enough space that we can put the arrows in. We had the negation of Q true until Q, and a negation of true until not true until Q. And finally we had not Q, a negation of true until Q, and then we were forced to put in true until the negation of true until Q. Seem to be getting some round brackets here where one should have set brackets. That's, I think it's good to make the notation consistent, and I would patch this later, but because the drawing's going to get a bit complicated, it's better not to patch it later, because it might be awkward to do that when there are more things drawn on top. Right, so those are the states, and now we want to consider the transition between the states. So for this, we go back to our they're up here. We go to our notes from lectures 8 and 9. So the states of the generalized non-deterministic bookie automaton are the elementary subsets. We've done that. And now the transitions. So they're labeled transitions. They're labeled by sets of atoms. And you have a transition from one elementary subset S to another elementary subset S prime wherever you can. So in every single possible place that you can, as long as it enjoys these satisfies these 4 conditions. The first condition just tells us what the set of labels is, and the next 4 constrain whether or not we can have a transition. The first 2 don't concern us with this exercise because they're to do with the next operator, but the last 2 do, and the last 2 say that if we have an until operator in a state and it's not yet been released, in the sense that the destination state on the right of the until, the destination formula is not currently true, well then the until operator needs to persist to any state we move to, because we can only not be the until operator it needs to stay, is going to have to stay true until eventually psi prime becomes true. And also, if we have the negation of an until operator, and the first part of the left-hand side of the until operator is currently true, so why is this true? So then the negation right, so because psi is true, if the until operator were true in state S prime, and if psi until psi prime were true in state S prime that we're about to move to, and psi is true now, then psi until psi prime would also be true now, because psi is true now, and when we move to S prime, psi will still be true until psi prime eventually holds. So if psi until psi prime were true in S prime, then psi until psi prime would be true now. So another way of saying that is, if the negation is true now, then the negation needs to be true in S prime. Right, so now having looked at those rules, so basically what we're going to do is from every state, we're going to see what transitions where we can make transitions from and to. So let's look at this state first. So let's see where we can have transitions out of this state. Well, true until Q is true here. Let's have a look again at the rule. So this rule would apply, so true until Q is true here. This rule would apply if if not Q were in the current state. But we don't have not Q, we have Q, so that rule doesn't apply. Here we have true until not, so true until psi, where psi is not true until Q. And we're asking, is not psi true? And it is here. So not psi is here true. So that means that the until operator, this until still needs to be true in any state we move to. So from this state, the only constraint is that we can move from this state to any other state in which true until not true until Q is still true. So that's this rule here. Sorry, not this rule. This rule here, this one. We've got an until here. It's the negation of the destination is in our state as well. So we need to keep the until operator. So that means this state can move to itself because the until operator is this until is still there when it moves to itself. And it can move to any other state in which, so it can move to here, and it can move down to here. Okay, let's go to this one. So again, this is similar. We've got true until not true until Q, as we had here, and again true until Q. So this one can also only go to states in which true until not true until Q is still in the state. But this time we've got true until Q and also not Q, which means that also true until Q needs to be true in any state we move to. So we can move to any state in which this formula, true until Q, and this formula are both in the state. So again, we can move to ourselves, we can move back to the same state, and we can move, in this case, back to this one. And all the others, these are the only two states that have both until operators not negated, so we can't move from this to anywhere else. Okay, so here we have another true until Q with not Q in it. So again, true until Q needs, if we're moving out of this state, we need to keep true until Q. And we've got the negation of true until this. Let's have a look at the rules for the negated until operators again. So the rule for a negated operator says if we've got the negated thing and the left-hand formula of the until belongs to S, which it does because it's true. So the true does belong to S. I didn't write it down, but it does belong, but it is there. So the negated until, when psi is true, always needs to persist. So we can only move to an S prime that keeps the negated until. So let's go back to here. So the negated until stays, and also the true until Q state stays in this case because we've got the not Q. So this can only move to states that again have true until Q and the negation of true until not true until Q. So it can again move to itself and true until Q, so it can also move down here. Okay, so here we've got true until Q. We don't have not Q, so there's no constraint at all on where this can move to because of true until Q. But again, we have the negated true until not true until Q, so we need to keep that formula. So this state can move to any state that contains this negated big formula. So it can again move to itself. It can move back to here. And those are the only two states that have that negated formula in. So we've only got one more state to consider. Now we have two negated until, sorry, no we don't. We have one negated until. This needs to right, so we have one negated until, we need to keep that. And we have an until, but we don't have the negation of this formula. So there's no constraint from that. So we've got a negated until, we need to keep that. So we can move from here to any state that has not true until Q. And that is the only state that has not true until Q. So this maps to itself. Okay, and we haven't put the labels on yet, but the labels are sets of atoms, and they are there's always the set of atoms that are atoms in the original formula, that occur in the original formula. There's the set of those atoms that are in the source state of the arrow. So there's the state from which the arrow starts. So this one is singleton Q. So all the arrows coming out of this state are singleton Q. Here it's the empty set because we don't have any positive atoms occurring, so empty set. Oh, sorry, we missed one of the arrows coming out of this state, so singleton Q. Here again, there's no atom occurring positively, so it's the empty set. here we've got Q, so we've got singleton Q. Here we've got Q, so singleton Q. And here we've got the empty set. Okay, so those are the labels. So we've now completed the transitions. Now we now need the initial states. So the initial states are all those states that contain the formula for which we're building the automaton. So in our case, we were building the automaton for not phi, where not phi was our original formula. So it's all the, so we want all the states containing not phi. Let me put these, just to make it clear, I'm going to put that these are different transitions. So I'm going to put the arrows into the initial states. I'm going to put them in purple. So it's all those that contain the formula not phi, where phi was true until not true until Q. So in the negation of that is in this state. So this is one initial state. And here we've got another initial state. So we seem to have two initial states here. And if we go back, so we've done the initial states, and now we have the final states. Now, for every until, it's a generalized non-deterministic Bookey automaton. So for every until formula, we have a set of final states. Every until formula that occurs in the complemented subformulas of phi. So we're going to have, in our case, we've got two until formulas. The formulas are, if we go to our complemented subformulas, so our two until formulas are this one and this one. So we're going to have accepting states for the large until and for the small until. We're going to have two sets of accepting states. So let's use some colours for them. So I'm going to have, let's say, green and orange. So green will be, this is going to be accept final states for true until not true until Q, and orange final states for true until Q. So we're going to have two sets of final states, and so for each one, so for any formula of the form psi until psi prime, the final states for that formula are all those that contain psi prime or the negation of the whole until itself. Okay, so if we go back to here, so our green states are going to be all those that contain the right-hand formula, the psi prime, or the negation of this big until. So our green accepting states are going to be this one, because it contains the negation of the until, and this one, because it contains the negation of the until. And also if any state that contains the psi prime, so that's not true until Q here. So also then this state is a green state because it contains not true until Q.
and neither of these are, because they don't contain either of those two formulas. So for the orange states, we're going to have all those states that contain Q, and all those states that contain not true until Q. So let's go to orange. So all those states that contain Q, so this one is orange. Because that contains Q. This one is orange because this one contains Q. Whoops. And also every state that contains not true until Q is also orange. So this one is orange because this contains not true until Q. Okay, and that is it. This here is our generalized non-deterministic Bookie automaton. So it's quite complicated, but not horrendous in how complicated it is. Okay, so we've got that. Let's go back to our question. So we've constructed the generalized non-deterministic Bookie automaton A not phi, but now let's simplify it by removing unreachable states and superfluous acceptance conditions. Let's see what that means. So let's go back here. So let's consider this generalized non-deterministic Bookie automaton. So run of this will start at one of the initial states. There are two initial states, this one and this one. And it'll run through the automaton, and the run will be accepting if it goes through infinitely many green states and infinitely many orange states. So we notice that if we've only got these two starting states. Any run from here, it can go around these loops, it can go backwards and forwards. It can never reach any of these three states because there are simply no transitions out from these two states to any of these three states. So these three states are absolutely irrelevant to the automaton because runs simply can't pass through them. So we can immediately simplify the automaton by throwing these three states away. So we're left with two states, and again we've got these two acceptance conditions, and a run will be accepting if it goes through infinitely many green states and infinitely many orange states. But since there are only two states in the two states we've got left, and both are green, any run will go through infinitely many green states. So the green states are serving no purpose. So we're left only with the only interesting acceptance condition is the orange one. So the simplified automaton is this. Let's put there's enough space here because it's very simple, but let's maybe expand a bit. So the simplified automaton so we're going to have this state and this state. I'm going to call them Q0 and Q1. Just to avoid writing the whole sets out because it doesn't matter what you call the states. So it's Q0, let's put Q0 on this side, and Q1. and we have, this is Q0 here. It's got an empty set transition to itself. That's remember, the alphabet are sets of atoms. And we've only got, the only atom we've got is Q, so it's either the empty set or the singleton. So an empty set transition to itself and an empty set transition to the other one. Q1 had a singleton Q transition to itself and a singleton Q transition to Q0. So here we've got Q, the propositional atom. Here Q0 and Q1 are names of states of the automaton. That shouldn't be confusing, but it's slightly unfortunate that I chose the same letter. The initial states, both states are initial. Let's keep that purple. And we're only interested in there's no point having the green acceptance condition, so we're only interested in the orange one, and that's the state Q1. So orange means accepting. So orange means final. And what I want to remark is that, let's do it in. So this is an NBA. It's a non-deterministic Bookey automaton. It's not a generalized one because we only have one set of final states. So very conveniently, we don't need to do anything complicated to turn this generalized non-deterministic Bookey automaton into an ordinary non-deterministic Bookey automaton, because we've already fortuitously got one. Right, so that completes part D. So now we go to look at the question. And now we want to construct the product of the resulting non-deterministic Bookey automaton with the transition systems below. So let's do that. So we remember that the product automaton, you take the transition system and you pair the states of the transition system to the states of the automaton that have the same set of atoms associated with them. So let's see, how can so in this case we're going to have our states S0, S1, S3 and S2. Let's just draw them out in the same way that we've got them here. So we're going to now to question E. I just need to remind myself where the states are. Right, so S0, S1, S3, S2. So we're going to have
S0, S3, S1, S2. Let's just check again the picture. S0, S1, oh dear, S1, S3, S2. I do want to keep, sorry about this. S1, S3. And for each state, we can pair that state with all the states that have the same in the bookie automaton that have the same set of atoms. So S0, if we go back to the preview, S0, S3 and S2 had the empty set of atoms. And our bookie automaton, this one has singleton Q associated with it because the transitions coming out are singleton Q. Or if we look up here, it had Q as the atom. I mean, really, Q1 is short for this set here that contains the atom Q, whereas Q0 is short for this set here, which does not contain the atom Q. So this has the empty set of atoms, and also the transitions out, therefore, are labelled with the empty set. So Q0 is associated with the empty set, and it's the only state in our bookie automaton that's associated with the empty set, and Q1 is associated with singleton Q. So these three were the empty set, so these are forced to be paired with Q0. We have S0, Q0, S3, Q0, S2, Q0, and S1, Q1, because S1 had, at least I hope so, let's go back, yes, S1 had a Q. Right, so now we have a transition from one state to another if and only if there's a transition in the transition system that from S0 to, so in this case from S0 to S3, and there's a transition in the bookie automaton. But here we're in a rather nice simple picture in that there is always a transition in the bookie automaton. So basically, it's just a question of where there are transitions in the original transition system. So the transitions were from S0 to S3, from S0 to S1, from S1 to S2, from S2 to S1, from S3 to S2, and from S0 to itself. And I think that's the correct picture. Let's have a look. Yes, indeed. And the labels are inherited from the bookie automaton. So all the Q0s transitions all have empty set. All the transitions out of the Q0 state have empty set, and this one has Q because that's out of Q1.
Okay, so we still need to define the accepting states and the initial states. Let's do the initial states first. Let's go to our notes on, so I've been doing this without consulting the notes, but if we go to the product, so this, I was following this description of the product, but just explaining it. We've done the transitions, so our initial states are, we need the initial state from the transition system and paired with all initial states from the automaton. But both states of the automaton were initial, and our final states are just all those states that were final in the where the automaton part is final. So let's go back here. So the initial states were any states that were both initial in the automaton and were from our starting state of the transition system, but the starting state of the transition system is S0. So our initial state is, I'm going to again do this in purple, is S0. And final states, all states that are final in the Bookie automaton. So Q1 is final in the Bookie automaton, so all the states with Q1. So let's go. Oops. So this is final. Right, so that's the first product automaton. And the second one, we have a very similar picture. We have a very similar picture, only the Q is in a different position. So let me just very quickly draw this one without making too much fuss over it. So now, so for the next one we have T0, T1, T3, and T2. And this time we can, the Q is over here, so T3 gets paired with Q1, and the others are all empty, so these get paired with Q0. Again, we have transitions wherever there's a transition, both in the transition system and in the automaton, but because there's always a transition in the automaton, it's just the same as the transitions in the transition system. So here we go to here. I don't like that arrowhead, so I'm going to so again, the labels are inherited from the Bookie automaton. So we get empty set wherever there's a Q0, wherever there's a transition out of a Q0. And singleton Q whenever there's a transition out of a Q1. And the initial state is again here. And the accepting state, the final state, is here. because Q1 was the final state. Okay, so these are our two product automata. So that's question E. And finally, let me write it down and then we'll move to see what we need to do. So finally, question F, we go to, so we want to show how the product automata can be used to model check the formula phi in the two transition systems above, with a counterexample path being extracted in the case that phi is false. Okay. So we want to model check phi. So we constructed, well, we've done what we needed. We constructed the automata for not phi. And formed the products with the transition systems. So we need to check the emptiness of the product automata. So we need to check for emptiness, meaning does the automata recognize the empty language? The emptiness of the product automata. So we'll do the first case of the first transition system first. So the first transition system is here. So what we're looking for is, does there exist a lasso that contains an accepting state? And there are various ways of finding one, but an easy way to get to a lasso here is we're at the start state, we go down here, and then we go around this loop. And we have a final state in the correct place. So it just needs to be somewhere in the loop, and it is. So indeed, so the product automaton in this case contains a lasso which goes from S0 Q0 S1 Q1 S2 Q0 and then back to here where S1 Q1 is final. Right, so this is this lasso. Therefore, phi is false
along the path S0. So now we want a counterexample path from the transition system, and we simply take just the transition system states out of this lasso from the product automaton. So along this path through the transition system. So if we go from S0 to S1 to S2 back to S1 and keep on going around that loop, phi is false. Let's have a look at that. If we go to the original automaton, so we're going S0, S1, S2, and back here. Remember, our original formula was saying at some point in the future, it's never the case that further in the future Q is true. But that's not true on this path, because we're going here, Q is true, it's not true, but then it becomes true again, it's not true, becomes true again. So Q is true infinitely often on this path, so we never get to a state at which, at some point in the future, Q is never true again. Okay, so our verification has been successful. Of course, in this case, we could have seen this from the start very easily, but the point is that this is an algorithm that will work for very complicated transition systems as long as a computer does it for us. Right, so let's look at the second transition system. So we're now dealing with this product automaton. And again, we're looking for, does there exist a lasso in which the loop contains an accepting state? So we need to find loops basically and make sure they're reachable from our starting state. So the loops here are, well, we can go around this loop. This does not contain a final state because the only final state is down here. Or we can go around this loop, but there aren't any other loops in this automaton. So none of the loops contain a final state, therefore there is no lasso. Now in practice, one can find the loops using a depth-first search, for example. So that's how an algorithm would do it. So it's a perfectly algorithmic process to find these loops and check for lassos. So we need to look for reachable loops. Is there a reachable loop that contains a final state? That's basically the question. So in this case, there isn't. So there is no lasso in which the loop contains a final state. So therefore, phi is true along every run. So we have successfully verified that the formula phi holds in this transition system. So there is some point in the future, whatever run we take, there is some point in the future from which Q will never hold again. So either we go around this loop, or one way or the other we end up eventually going to this loop, and in either case, from some point in the future, Q will never hold again. Right, so that completes the exercise. I hope this was helpful for you. It's a bit different from the usual lecture. Next week, as I have already said by email, we're going back to, well, ordinary video lectures, I suppose, as the new norm for the lectures on this course. And we're going to be starting a new subject, which is program verification.
Okay, so in the meantime, I hope you're all keeping well, and I wish you all a pleasant May holiday. Okay, bye for now.